Carbon is one of the most important elements in nature. Our life on this planet is carbon-based. It's largely because of the versatility of the carbon bond. Carbon has four valence atoms, 4 valence electrons, I should say. And it can engage in all kinds of chemical reactions, and even the carbon elemental form, so basically just carbon itself, can exist in a whole variety of different forms. No other element found in nature under normal temperature and pressure will exhibit elemental forms with such variation. Carbon is the most colorful form of element in this respect. So let's take a look at carbon as our example of covalent solids. What kind of forms can it assume, can it exist if you just have a bunch of carbons, no other elements involved? Well, we have some famous examples. Diamond is our first example. This is one way for elemental carbon to exist. The crystal structure of diamond is like this. You have a whole bunch of carbons, okay, just carbon itself, nothing else. And each carbon is linked to 4 nearest neighbor carbons. So here's the carbon at the center. Here's 1, 2, 3, 4 nearest neighbors. And that makes sense because, you know, each carbon needs 4 extra valence electrons to complete the shell, so it contributes 4 electrons of its own to and share 1 extra valence electron with each of these 4 neighbors, so everybody's happy that way. And the crystal structure is such that these 4 nearest neighbors have the same distance relative to each other. Okay, 1, 2, 3, 4, 5. All these are equal distant. So these 4 nearest neighbor carbon atoms form what's called a tetrahedron. A tetrahedron is such a structure that you have 4 points in space, and the distance between each point to every other 3 points is the same. It's called a tetrahedron. At the center of each tetrahedron is another carbon atom. So the structure is very symmetrical. And this bond is quite strong. Not only so, this guy bonds to here, and it bonds to here, bonds to here. Every carbon atom is attached to every other atom in entire structures through all these multiple bonds. And the cohesive energy, which is the energy it takes to break a carbon atom pair, is 7.37 eV. That's also pretty large. Diamond, as you know, is quite an interesting material, not only because we can use it as jewelry and so forth, but also it exhibits some of the most amazing physical properties. For example, diamond is the strongest material found in nature. Nothing is stronger than diamond. We're talking about naturally found materials. And we can understand that because the bonding is very strong, and when you try to push on one atom, you actually push in everybody else. You push its neighbor is pushing its other neighbor, and so on. So that makes the entire structure extremely solid, extremely strong, and therefore covalent solids are among the strongest solids, strongest materials in nature, and diamond being the strongest of them all. And because of its very strong bonding, you can think of each bond as effectively as some sort of a spring, and the spring has very strong spring constant, right? Because the bond is strong. And so if one of these atoms shake for whatever reason, if this atom is tied to another atom with a very strong spring, the spring will immediately send that vibration information down to the other particle. So this guy starts to shake as well, and this guy starts to shake as well, and so forth. Okay, so just imagine a whole bunch of spheres interconnected by a series of very strong springs. If you shake one of them, the neighbor will know immediately, and so on. So the entire vibrational information will travel down this chain very quickly. This means what? This means diamond has excellent thermal conductivity as well as very fast speed of sound. Thermal conductivity, what does that mean? If you expose a certain part of the diamond to a high temperature, that will cause these atoms near the high temperature source to shake. Right? And then because of the strong bond, the next neighbor knows that immediately, and the next neighbor knows that immediately. So heat is propagated very quickly over. So you have a large thermal conductivity. The coefficient of thermal conductivity for diamond is 33.2 watts per centimeter per Kelvin. You know what that you know what that number is? That's the highest thermal conductivity than any other solids. Much better than gold and silver or copper, even though those are also excellent conductors of heat. Diamond is much better than those. So diamond can actually be used as a cooling material for computer chips, even though you may think, gee, that costs too much money, right? But there are researches going on that use industrial diamond, industrial quality diamond, not gem quality diamond. Okay, industrial quality diamond costs a lot less. Researchers are going on to use these materials to cool down the heat generated by computers. So the efficiency of the cooling will be much higher, and that's one of the bottlenecks for designing high-performance chips is that it may generate too much heat so it can fry itself. But with diamond as cooling materials, this problem can be resolved. So we may see diamond-cooled computer chips in the near future. And also, the speed of sound is very high because, again, you shake this atom, its neighbors know immediately because they're linked by a very strong spring. Okay, the speed of sound in diamond is an astonishing 12,000 meters per second. That's several times the value of the speed of sound in water, and much, much higher than 340 meters per second, which is the speed of sound in air at room temperature. Now, what about the optical properties? Diamond is very shiny, very brilliant, and that is because diamond has an extraordinarily large value of index of refraction n. So you have a beam of light coming in. If you cut the diamond facets cleverly, then they can easily undergo total internal reflection before coming out. So most light get reflected back towards the source, therefore it looks brilliant. But to a physicist, what's really interesting for diamond is its other properties: mechanical property, optical property, acoustic property, and so on, and electrical property. In terms of electrical property, what do you think? Do you think this is a conductor or an insulator? Well, a conductor would need what? Moving electric charges, right? No electric charges are mobile. All the electrons are locked up inside the atom or between the bonds. They cannot go anywhere. Therefore, diamond is an insulator. Except in a special case when you dope diamond with certain other ions, it is possible to turn it into a semiconductor, but that is a very rare case. Pure diamond is definitely an insulator. Now let's turn into a much cheaper form of elemental carbon, and that is graphite. Chemically, graphite and carbon, they're both made of just carbon atoms and nothing else. What makes the difference between graphite and diamond? They look very different. Okay, diamond is strong and shiny. Graphite, on the other hand, is smooth, slick, and not very strong. It's the way the atoms are tied together. In graphite, you have sheet-like structures. Within each sheet, each carbon atom is tied to three immediate neighbors, 1, 2, and 3. And they form hexagonal rings, 1, 2, 3, 4, 5, 6, six-sided polygons called hexagonal rings like this. So it's like this. So here's 1, 2, 3, 4, 5, 6. You got 6 carbon atoms at each corner, one at each corner, and this structure extends. Okay, it extends. So you have it's like a honeycomb structure. Within the same sheet, the bonding is quite strong. And also the electrons. Some of the electrons are not just connected to trapped here. They can actually move from place to place within each sheet. So graphite is pretty strong in this sheet, and it can conduct electricity and heat quite well because of these electrons hopping around between bonds. So within this plane, it's a good conductor of both heat and electricity, and is relatively strong. However, between sheets, the bonding is much weaker. There are bonding between different sheets, but that's much weaker, which means you can easily slide one sheet against another. That is why graphite is a very slick material, because of the relative ease to move one sheet against another. they can actually be used as a lubricant for this reason. So it's a lubricant, and also, relatively speaking, it's a reasonably good conductor because electrons can go from here to there. But the conductivity, electrical conductivity, and thermal conductivity, they're both anisotropic, or even acoustic properties are anisotropic. Sound can easily propagate this way, but not easily that way, because of the anisotropic nature of the crystal structure. Okay, you know what isotropic means, right? It means the same in all directions. Anisotropic means it behaves differently in different directions. Very fast conduction here, very slow conduction there. And graphite has many important applications as well, even though they're not as expensive as diamond, because graphite is a very common material. Diamond, on the other hand, you do not find gem quality diamond very easily in nature. But even though graphite and diamond are the two most common forms of elemental carbon that everybody knows, there are lesser known forms of elemental carbon, and even though they're lesser known, they're just as important, if not more. I have here another example of elemental carbon. It's called Buckminster fullerene, otherwise known as the buckyball. There is, in fact, a whole class of materials called fullerenes. Fullerenes. All these fullerenes share something in common. They're all made of carbon atoms, nothing else, just carbon atoms. And these carbon atoms band together to form a certain geometrical shape. That shape can be a sphere, it can be a tube, can be an ellipsoid. Okay, a sphere, a tube, or an ellipsoid, three-dimensional structures. If that's the case, we call this material a fullerene. There are different types of fullerenes. The buckyball is a spherical fullerene in which you have basically a ball of carbon atoms. How many carbon atoms are there on the surface of this ball? 60. We call it C60. The name Buckminster fullerene came from the people who discovered it first. It was discovered in 1985 at Rice University, and the scientists named it Buckminster fullerene in honor of an architect, in fact, not a scientist, an architect by the name of Buckminster Fuller. His first name was Buckminster, his last name was Fuller. Buckminster Fuller designed a lot of interesting geometrical shapes in architecture, including one form called geodesic, which kind of looks like this C60 structure. That was before C60 was ever discovered, okay? So these scientists named their discovery Buckminster fullerene. And later on, scientists found that there are other ways to tie carbon atoms together to form, an ellipsoid or even a tube. And all these things are called fullerenes, even though Fuller himself was not really a material scientist. It was just for historical reasons. C60, just like any other fullerene, is a very versatile material. And it's relatively newly discovered, 1985. That's the first fullerene ever discovered. These materials are the subject of intense ongoing scientific and industrial research. They are of great interest not only to theoretical physicists, they're also of great interest for industrial applications, because if there's only one word I can use to describe all these materials, that would be versatility. We can think of all kinds of applications for buckyballs and for other fullerenes. Take a look at buckyballs. The electrical behavior. This thing can be a semiconductor. It's actually a semiconductor at room temperature. It also becomes a superconductor when the temperature is low enough. And the theory of why this buckyball is a superconductor, at what temperature does it become a superconductor, and so on, the theory is not entirely established yet, so it is an ongoing research. The mechanical property is also very interesting. It's kind of soft at room temperature and normal pressure, but if you compress it to about 70% of its volume, it transforms itself into a very hard form of diamond. Okay, so it's got interesting mechanical properties as well. And what can we do with this buckyball? What kind of applications can we think of? Well, there are all kinds of possibilities. In energy research, for example, this thing can be used in photovoltaic devices. Photovoltaic device, what's that? That is a device which takes energy from the sun, light energy from the sun, and turns into electricity. We call it photovoltaic devices. Fullerenes, such as buckyball, they absorb visible light. Unlike ionic crystal, these guys absorb visible light, and they turn visible light into energy. So you can use them in photovoltaic devices. And this guy also has interesting chemical properties in the sense that it can bond with hydrogen without alternating the hydrogen structure. This means I can use buckyballs, Buckminster fullerenes, to bind with hydrogen in large quantity. Why is that so useful? Because the hydrogen fuel cell requires a medium which can store a lot of hydrogen without using too much of a size. You don't want to use liquid hydrogen because it's explosive, and you do not want to use hydrogen gas because that you don't have a whole lot of hydrogen concentrated in the same spot. So fuel cells that can power future cars with zero emission would require a medium that can store a lot of hydrogen in a very compact region, and buckyball would be a good candidate for that as well. You can also use it in medicine. Okay, this guy, there is a, it's hollow inside, right? You can trap some molecules inside. These molecules would otherwise be volatile. They can, they can expire. They can have chemical reactions, whatever. But you can trap it inside. You can, then it becomes very stable. You can transport medication with buckyballs, and this thing also turns out can be used to fight the HIV virus because of the unique shape. It can actually block a certain enzyme which is very active in the HIV virus replication. So this is a potential anti-HIV drug as well. So, needless to say, because of its unique, because of its versatility, there's still active research going on for these buckyballs. The buckyball is not the only fullerene. There is another very famous example, even though it's not the only other fullerene in there, and that's called the carbon nanotube. Just like the buckyball, the carbon nanotube is also made of hexagonal structures of carbon. And then this time we do not form a geodesic sphere, rather we roll that sheet around to form a tube. Okay, it's quite long this way and relatively thin that way. This picture is a little misleading. In reality, it's much longer this way. And this is a single layer. You can also have multiple layers. There are different types of carbon nanotubes. What do we call nanotubes? Because the size here and there, we're talking about order of around a nanometer. Carbon nanotubes. Carbon nanotubes are one of the most interesting materials people have ever found. It certainly is the most versatile material discovered in recent years. It might be the most versatile material ever discovered by humans. Why do I say that? Well, look at the mechanical properties. The carbon nanotube, along the direction of the tube, is an extremely strong material due to the tight bonding between the neighboring carbons. So strong that it's got a tensile strength of about 60 gigapascal. What does that mean? It is 100 times as strong as steel. Okay? This number here, 442,000 kilograms, is the weight of a giant 747 jumbo jet fully loaded. It can take off at this weight, about this weight, maximum takeoff weight. Did you know that you can hoist an entire 747 up when it's fully loaded with one single cable made of carbon nanotubes, as long as the tube is about as thick as this pen? It's about as thick as this pen. That's all you need to support the entire weight of a fully loaded 747. No other materials we discovered can possibly do that. It is stronger than diamond, even though diamond is a naturally found material. This is more or less artificially made. So you can imagine what kind of application we can take advantage of. Using this as the strongest material, we can build cars that are virtually indestructible, we can also use that for armor, for shield in military applications. You can think of so many different applications just because of the mechanical property. And one of the novel applications, possible applications that scientists are thinking, is to build what's called a space elevator out of carbon nanotube materials. The space elevator would be a giant shaft rising from the equator all the way to about 1/3 of the way to the moon. Okay, it's called a space elevator precisely for that reason, because we can just, if you want to go to space, we don't launch anything anymore. We just push a button and the elevator just takes you there. This elevator must be made of very, very strong materials and nothing else but carbon nanotubes. That's, of course, in the future, but hopefully it is in the near future, not the far future. It is not far-fetched. It can be done. And it's got also interesting electrical properties depending on how the specific form of carbon nanotubes is, the different types of carbon nanotubes. It can be anything between an insulator to a very good conductor. So it is very versatile in electrical property. We can tune it so it becomes different types, whether insulator, semiconductor, or a very good conductor. The thermal properties are very anisotropic, just like graphite, because it's easily conducting this way, but between tubes is not easy because the link is weak. And it's also got interesting optical properties. We have some research going on to turn the carbon nanotube into some sort of a display, computer display or TV display. And we also have applications in energy research. We can store hydrogen atoms, hydrogen within the hollow part of the tube, so it can be used as a medium for energy fuel, and so on and so forth. This is, like I said, the most versatile material ever discovered in recent years, or maybe forever. And therefore, there's so many things we can say about this. I would really encourage you to do some more research of your own on this to see whether you get interested. If you get interested in this, in materials like this, there's so many things you can do to turn this into into a research career if you choose to, or even if you don't choose to do a research career, there may be so many things that you may encounter in your career which may have to do with carbon nanotubes, and this is only the beginning of this very exciting field.